In this lecture, let us see how to analyze a continuous beam which is having sinking of supports using moment distribution method. So the problem is to analyze a continuous beam shown in figure. Support B, this is support B. Support B sinks by 5 mm. Take Young's modulus E equal to 2 into 10 power 5 Newton per millimeter square and I equal to 10,000 centimeter power 4. So here span is 3 meters, here span is 6 meters and here 3 meters. UDL over spans AB and BC. Central point load in span CD. Moment of inertia for AB is I, BC is 2I and CD is 1.33I. So the first step will be stiffness and relative stiffness. So with regard to stiffness, write the span first. So we have span AB, span BC and span CD. So AB, BC, CD. Then write the length or span. So AB 3 meters, BC 6 meters, CD 3 meters. Then write the moment of inertia. Moment of inertia of AB is I, BC is 2I and CD is 1.33I. Then stiffness. A is fixed, B is continuous. Therefore, I divided by L, I by 3. B is continuous, C is continuous. Therefore, I by L, I is 2I and L is 6, so 2I by 6. In CD, C is continuous whereas D is freely supported. In case we have freely supported ends, then we should use 3/4 of I by L. So 3 by 4 into I. I is 1.33I and L is 3. So here to find the relative stiffness, we are multiplying by 3 and dividing by I throughout. So if you multiply by 3 and divide by I, you will get 1. 3 by I, so you will be getting 1. Here 3 will get cancelled. 3 by 4 into 1.33. So this will be 1. Then step 2, distribution factor. Distribution factor dFAB equals 0 since A is fixed. dFBA equal to stiffness of this member divided by sum of stiffness of members meeting at the joint B, that is BA and BC. Therefore, dFBA equal to KBA by KBA plus KBC. Similarly, distribution factor BC equal to KBC by KBA plus KBC. And distribution factor for CB will be KCB divided by KCB plus KCD. And distribution factor for CD will be KCD divided by KCB plus KCD. And distribution factor for DC will be equal to 1 since it is freely supported or hinged. If it is on roller, we should also use the same value, that is 1. Distribution factor should be 1. So the distribution factor calculated accordingly. So we are getting 0.5, 0.5, 0.5, 0.5 and 0.5 and finally 1 since D is freely supported. Then the third step will be fixed end moments. So span AB is subjected to UDL, therefore fixed end moments will be minus WL squared by 12 and plus WL squared by 12. And span BC UDL minus WL squared by 12 and plus WL squared by 12. And CD we have central point load, therefore minus WL by 8 plus WL by 8. Therefore using the formula we can calculate the fixed end moments. Say minus WL squared by 12 plus WL squared by 12 minus WL squared by 12 plus WL squared by 12 and minus WL by 8 plus WL by 8. So this is the fixed end moment due to the applied load alone. In this problem, we have sinking of supports. We have sinking of support. That is support B sinks by 5 mm. It is given in the problem. So in case we have sinking of supports, then fixed end moment due to sinking need to be found separately. Therefore, fixed end moment due to sinking and fixed end moment due to sinking is given by plus or minus 6 EI delta by L squared. So in case of span AB, MF dash AB equal to MF dash BA equal to plus or minus 6EA delta by L squared. We are using minus 6EA by delta by L squared since minus sign is due to sinking of supports towards right side of the span. So in span AB, if you take span AB, in the right side only we have sinking. So if you have sinking at the right side, then this will be negative. If you have sinking at the left side of a span, then this fixed moment will be positive. So minus sign due to sinking of support at the right side of the span. And before calculating this, we need to have the value of EI. So E is 2 to 10 power 5 Newton per millimeter squared. Moment of inertia is 10,000 centimeter power 4 converted to millimeter power 4. So that multiply by 10 power 4 will be getting 2 into 10 power 13 Newton millimeter squared. So if we want to have in kilonewton meter squared, divided by 1000 and divided by 1000 squared. So altogether we need to divide by 10 power 9. Therefore 2 into 10 power 4 kilonewton meter squared will be the EA value. So we need to substitute the EA value here. Delta 5 mm sinking, it need to be used in meters. Therefore 0.005 divided by L square. Therefore we'll be getting MF dash AB equal to MF dash BA equal to minus 66.67 kilonewton meter. Then fixed moment in span BC will be MF dash BC will be equal to MF dash CB equal to plus 68 delta by L square, since the sinking is at the left side of the span. So if we see the sinking, so in span BC, sinking occurs at B. So with regard to BC, the sinking is to the left side of the span. If it is to the right side of a span, then minus 68 delta by L squared. If the sinking is to the left side of the span, it should be plus 6 EA delta by L squared. We have EA value and delta, and we should be very careful in substituting the value of I. So in span AB we had only I, whereas in span BC we have 2I. So E into 2I need to be substituted here. So it will become 12 EA delta by L squared, and then substitute the value of EA which we have calculated earlier in kilonewton meter squared, and delta should be in meters. Therefore we'll be getting 33.33 kilonewton meter. And coming to span CD, there is no sinking, therefore there will not be any fixed moment due to sinking. So here we need to mark the fixed moment due to applied load like this. So here minus 9, plus 9, minus 36, plus 36, minus 30, plus 30. And fixed moment due to sinking is minus 66.67, minus 66.67. This is for MF dash AB and MF dash BA. And this is 33.33 and 33.33 we got for BC, and 0 here. So we need to add at the support point. So minus 9, minus 66.67. Plus 9 minus 66.67, minus 36 plus 33.33, plus 36 plus 33.33, minus 30 plus 0, 30 plus 0. That will be the final or combined fixed moment. So this combined fixed moment value only need to be used for the moment distribution process. So step 4 will be moment distribution. Joint, we have joint A, joint B, joint C, joint D. In A we have only one member AB. In B we have BA on the left side, BC on the right side, CB on the left side and CD on the right side. For D we have DC. Then write the relative stiffness, everything is 1. Then write the distribution factor 0, 0.5, 0.5, 0.5, 0.5, 1. Write the fixed moment minus 7.5 here, 75.67 here, minus 57.67 here, minus 2.67 here, and 69.33 here, and minus 30. This is the combined fixed moment which we obtained in the previous step. And at this point we should note whether there is any free support in the continuous beam. So in this problem, support D is freely supported. So initially it need to be balanced. So apply balancing moment. So balancing moment will be, if plus 30 is here, minus 30 need to be applied. And whenever we apply some moment at one end, half the moment will be carried over to the far end. So this is carryover. So carryover moment will be minus 30, half will be minus 50. Then we need to get the finalized fixed moment by adding this value. So minus 75.97 will be 67 will be there, and minus 57.6 will be here, and minus 2.6 will be here, 69.33, minus 30, minus 15, minus 45, plus 30 minus 0. Hereafter we should not use this n because we are closing this portion as we have balanced and made it 0 initially, which we should get final value. Therefore, we should not do any carryover or distribute at this end. So it is closed. Now, distributed end moment. With regard to distributed end moment, we need to consider every joint. So consider joint A. At joint A, we have minus 75.97 plus 75.97 need to be applied, and factor is 0, therefore 0. And here minus 56.67, minus 2.67. When we add these two, you'll be getting minus 60.34. So plus 60.34 need to be applied. This 60.34 multiplied by corresponding distribution factor will give you this distributed moment here. Similarly, 60.34 multiplied by this corresponding distribution factor will give you this moment. So 30.17, 30.17. Then coming here, 69.33 minus 45 will yield plus 24.33. Therefore, minus 24.33 need to be applied for balancing. So this balancing moment multiplied by corresponding distribution factor will give you the distributed moment. So minus 24.33 into 0.5. Similarly, minus 24.33 into this 0.5 will give you this. Next, this is one iteration. The next iteration should start with carryover moment. So carryover should be done between the members AB to BA, BA to AB. Similarly, BC to CB, CB to BC, CD to DC, and DC to CD. And CD to DC we should not do as we have closed the path. Similarly, DC to CD won't also come because there is no process here. So carryover moment, half the moment will be carried over here, half the moment will be carried over here, half the moment will be carried over here, and half of 30.17 will be carried over here. Here, there is no carryover process. Then distributed moment, second iteration. So at the joint A, we have 15.09 minus 15.09 need to be applied, multiplied by corresponding distribution factor will be 0. Then here 0 minus 6.09, so plus 6.09 is to be applied. This multiplied by corresponding distribution factor will yield this value. This multiplied with this will yield this value. Then coming to joint C, 15.909 is here, therefore minus 15.09 need to be applied. Minus 15.09 multiplied by this distribution factor will give you this moment. Minus 15.09 multiplied by corresponding distribution factor will give you this distributed moment. Then at this end, there is no process. Then again, third iteration, carryover moment. Half the moment will be carried over here, half will be carried over here, half will be carried over here, half will be carried over here. And here there is no carryover process. Then distributed moment. So consider joint. 1.53 is there. Minus 1.53 need to be applied. So multiplied by distribution factor is 0, therefore 0. Here we have 0 minus 3.78. So plus 3.78 need to be applied. Multiplied by 0.5 will yield 1.89. 3.78 multiplied by 0.5 will yield 1.89. Here we have 1.53 and 0. Therefore, minus 1.53 need to be applied for balancing. So this minus 1.53 multiplied by this 0.5 will give you minus 0.77. Minus 1.53 multiplied by 0.5 will give you minus 0.77. Then next carryover moment. Half the moment, half the moment, half of the moment, half of this moment. Here there is no process. Then again distributed moment. At joint A, 0.95 minus 0.95 need to be applied into 0 will give you 0. Then 0 minus 0.39 plus 0.39 need to be applied. So whatever the balancing moment, write within bracket and preferably in pencil. You need to write all these values in the bracket using pencil so that you will not get confused with finding the final end moments. So this multiplied by factor will give you this. Similarly, here 0.95 is here, balancing moment will be minus 0.95. Minus 0.95 multiplied by 0.5 will be minus 0.48 and minus 0.48. So we have completed 1, 2, 3, 4 iterations. So 4 iterations are enough. Then we can start from this finalized fixed end moment, add all the values, you'll be getting the final end moments. So this is the procedure need to be followed by moment distribution method. Then once the end moments are there, then we can go to analyze the shear force and bending moment.